and we'll see how this is motivated by this problem or this example that I talked about of having irreducibles which are not separable. Okay. So what is a perfect field? So let me just quickly define this. So suppose F is a field of characteristic P. Okay, this only makes sense, let's say, for characteristic P fields. P is a prime. So the computation that we just did with 3 actually works in general. Okay, so let's do the following. Let's take the map from the field F to itself. Let's call it phi, which is the following. It takes every element of the field and maps it to its pth power. Okay, P being a prime here. Now observe that this map is actually a field homomorphism. So claim or observation, fact, observe phi is a homomorphism of fields. Okay, well, what do we have to check? We just have to check that it maps AB, phi maps A plus B to phi A plus phi B. Okay, phi maps the product AB to phi A, phi B, maps inverses to inverses. Okay, it maps 1 to 1, right? Now observe that, well, I guess inverses to inverses is not necessary if you have checked that it maps 1 to 1. So let's just erase this. So we just need to check that phi satisfies these properties. Okay. Now, well, really these two properties are more or less obvious from the definition. If it sends AB, it sends AB to AB whole power P, which is A power P, B power P. So these two are more or less obvious. The only thing one needs to check really is this property. So let's do that. So let's compute A plus B whole power P. Okay. And observe, this is more or less like the computation we did with 3, which is there are 2 terms which are just A power P plus B power P, and then lots of cross terms which come from the binomial expansion. But all of them look like this. What are the cross terms? It's P choose R or PCR x power R. Well, not x here, it's A power something, B power the complementary exponent. This is R going from 1 to P minus 1. Now observe that this P choose R, this term over here, is in fact divisible by P. Okay, why? Well, what does this look like? This is a factorial of P divided by the factorial of R times the factorial of P minus R. And since R and P minus R are both numbers strictly between 1, I mean they are numbers between 1 and P minus 1. Okay, they are strictly smaller than P. So when you sort of write out this factorials, the numerator will have all numbers 1, 2, 3 till P. The denominators will again be like a product of some, it's a product of one factorial with the product of another factorial, but the bottom does not involve the term P. It only involves terms which are strictly smaller than P. Okay, so this P on the numerator will survive the cancellation. So at the end of this cancellation, you're still going to be left with this P. Okay, so P divides the answer. That's the point. So P divides this quotient, and so P choose R is a multiple of P. So therefore, so P divides P choose R implies that term is 0. P choose R, A power something, B power something is 0 in this field F. Why? Because F has characteristic P, and this is therefore, since this is a multiple of P, this is just the 0 element in the field F. Okay, so that's what characteristic P means, right? P times any element of the field is just 0. Okay, so therefore you're only left with the 2 terms at the end, A power P and B power P. Okay, so this just shows that phi is a homomorphism. Okay, and this has a name, so definition or notation, nomenclature, phi is called the Frobenius map. Okay, so we call this the Frobenius map of F. Okay, for each field of characteristic P, you have this map, A going to A power P. Okay, and observe that because it's a homomorphism between two fields, what you certainly know is that phi is injective, right? In fact, more generally recall, if I have a field F and I have a homomorphism from that field to any ring, think of both as rings, but if the left hand side is a field, then if the domain is a field, then any ring homomorphism is necessarily injective. So ring homomorphism from a field to a ring must be injective. Okay, why is that? Because the kernel, recall, is an ideal. Okay, so the kernel of this, let's call it psi, is an ideal of the left hand side, but a field has no ideals other than 0. Okay, so this means that, well, there's also the whole ideal, if you wish. Kernel of 0 can be 0 or the whole thing, but it can't be the whole thing because 1 maps to 1, right? It can't be this, since by definition a homomorphism is required to map 1 to 1. Okay, so any ring homomorphism is necessarily injective if you are going from a field to some other ring, because a field doesn't have any ideals. Now, since this Frobenius map phi is a map from a field to itself, what we therefore conclude is that therefore the Frobenius map from F to F is definitely injective. A going to A power P is injective. Okay, but and this is important to keep in mind, but not necessarily surjective. Okay, this need not be a surjection, and in fact that is exactly the example we just talked about. Okay, so if it seems slightly unfamiliar, notice that the example we just gave, so let's take the example p equals 3, let's take the field f to be f3 of t, where t is the indeterminate, this is the field of rational functions, and the Frobenius map, which is everything going to its cubed. So what is a map from f to f? It sends every alpha to its cube. Okay, so this is the Frobenius map. Observe that the image of this Frobenius map, does not contain the element t of the field. Okay, why is that? Because if it did, then there would exist, because if not, then you would claim that, you would conclude that there is some element of f such that alpha cubed equals t, and that is exactly what we just showed is not possible, right? You write alpha as at by bt and show that at by bt whole cubed equals t is impossible. You can't find such polynomials at and bt. Okay, so the example we just talked about is in fact something which shows that the Frobenius map is not a surjection. Okay, but at least it's injective in all cases. Now here's the beauty of this whole thing. So let's make a little definition here. If the Frobenius map is surjective, so we say that the field f is perfect. We say f is a perfect field. F is a perfect field if its Frobenius map is a surjection. Okay, if its Frobenius map is, well, if it's a surjection, it's already an injection, remember. So saying it's a surjection is the same as saying it is an isomorphism. Okay, so let me write it as a surjection, is a surjection, and hence an isomorphism. Well, isomorphism from the field to itself, so that's what we call an automorphism. Hence an automorphism of the field f. Okay, so if the Frobenius is surjective as well as being injective, then we say that f is a perfect field. Okay, so we have just seen an example of an imperfect field. The field f3 of t is not perfect because its Frobenius map is not a surjection. Okay, but are there examples of perfect fields? Well, there is one nice class of examples, obvious class of examples, which are just the finite fields. So let's look at FQ. Okay, any finite field. Okay, what is Q here? Q is some power of the prime P here, say P power M. P is the characteristic of the field. Okay, any finite field is necessarily perfect. Okay, here's an important example, which is any finite field is perfect. Okay, why? Well, recall the Frobenius is an injection, right? The Frobenius map from FQ to itself is always an injection. Is injective, but injective just means it's a one-to-one function. But if you have a finite field, then one-to-one automatically implies onto, right? You have an injective map from a set of some 10 elements. Well, 10 is not a power for prime. Let's say I have the finite field F16 from a set of 16 elements to itself. I have an injective map. Then that map also has to be surjective, right? So this is a consequence of the finiteness. So this implies phi is automatically surjective as well. Okay, because F is finite. Okay, this is of course not true if you have an infinite field. You cannot conclude an injective map is automatically surjective. So this is one example. Well, what are other examples of infinite fields which are necessarily perfect? Well, you can take algebraically closed fields. So here's the second example. So suppose F is any algebraically closed field of characteristic P. Closed field of some finite characteristic, let's say characteristic P, then this is automatically perfect. Okay, why? Because, well, this time the reason is slightly different. So let's look at the map phi from F to F, which is every element going to a power P. And we want to claim that this map is surjective. Well, what does that mean? Take any element of F, let B in F. The claim is that there exists an element A in F such that a power P will give me this element B. Okay, i.e., let's rephrase it as follows. This is the same as saying that the polynomial, so let's look at the polynomial x power P minus B. Okay, so look at this polynomial. It's a polynomial with coefficients in the field F. This polynomial has a root in F. Right, that's exactly what this element A would be. It would be a root of this polynomial. But F is algebraically closed and I have a polynomial with coefficients in F. Well, this is true because F is algebraically closed. Okay, the polynomial has a root, but this is true. This is true because F is algebraically closed. Okay, so you've now seen two examples of perfect fields. One are the finite fields and the other is the class of algebraically closed fields of finite characteristic. Okay, and what's the point of introducing this new notion? Well, recall all this began because we constructed an example. So we said, let's go back up. We said that over a characteristic 0 field, there we are. So if the field has characteristic 0, then a polynomial being irreducible implies it is separable. If the field has characteristic P, irreducibility does not imply separability. Okay, but here's the importance of this perfectness assumption. That's the little theorem or proposition for us, which is that if F is perfect, however, if F is a perfect field, okay, and let's assume the characteristic is called P. Let's say the characteristic is some prime P. If F is a perfect field, then the same fact holds. Then every irreducible is automatically separable. Every irreducible polynomial, f in fx is necessarily separable. Okay, so let's prove this. Okay, so what do we need to do? Let's take f to be reducible. So let f of x be an element of fx, be reducible. To show it is separable, we need to show that its derivative is not 0, right? So recall, need to show. So we already had this proposition that for an irreducible polynomial, separability is the same as derivative not vanishing. So need to show derivative of f does not vanish. Okay, so suppose not. Let's proceed by contradiction. Suppose not. Let's write. So suppose the derivative, say the derivative vanishes. Then we have seen this before in the earlier lectures on repeated roots. If the derivative vanishes, then it means that the only coefficients of f which survive are the multiples of p. Then f must have the following form. It should look like a0 plus some a1 x power p plus some a2 x power 2p and so on. Some, let's say, a r x power r, let's say a n x power np. Okay, this is the only way in which the derivative can vanish. In fact, if not df. Why? Because if you just compute the derivative, if you take x power r, what happens is it becomes rx to the r minus 1, and that term vanishing can only happen if r is a multiple of p. If r is not a multiple of p, that term doesn't vanish. So the only non-vanishing terms which can occur, the monomials which can occur in fx, are the ones x power 0, x power p, 2p, 3p and so on. Okay, so this again you've seen before. Now, so this is what we know, f should have the following form. But where does the perfectness assumption now come in? How does that help us? So recall, all these a0, a1 and so on are all elements of the base field, right? So all the ai's are after all elements from the field f, and f is known to be perfect, or f is assumed to be perfect. What does that mean? It means that the Frobenius map is an isomorphism, which means that for each ai, I can find a corresponding bi. I mean, I can find many of them maybe, but at least one bi exists. There exists bi such that ai is the pth power of bi. Okay, so this is for all I equals 1 to n. So what does that do for us? It enables us to rewrite the polynomial f as follows. So instead of a0, so this is for 0 to n. So instead of a0 here, I will rewrite it as b0 power p. Instead of a1, I will write it as b1 power p, x power p, and so on. bn power p, x power np. Okay, let's go up and check. This is how f looked. I've just changed all the a's into the corresponding powers of pth powers of the b's. And now, again, by the calculation we have done before, using the fact that the field has characteristic 0, this is just b0 plus b1x plus bn x power n, the whole power p. Okay. Now observe that this polynomial, now that we have written it in this form, this polynomial cannot be reducible. Okay. It is straight away obvious that f of x cannot be reducible. Well, why not? Because it factors obviously as the pth power of some other polynomial. This looks like some gx power p, right, where gx is some polynomial, and that means that f is not irreducible. Okay, so notice here that, by the way, that n is at least 1. So to begin with, f is not a constant polynomial, right? So I should have said n here is at least 1. The degree is at least p in some sense, right? You cannot have a constant f here because I've assumed f is irreducible to begin with. So the point is, the f has been shown to be a power of g, and that of course means f is not irreducible. Okay, that's a contradiction. So that proves what we wanted, which is that if I have an irreducible polynomial with coefficients in a perfect field, then that polynomial is automatically separable. Okay, and so as some consolation to the failure of separability in general for irreducibles, if characteristic of the field is 0, or if the characteristic is p but it's separable, or f is perfect, sorry, if characteristic of f is 0, or if f is a perfect field, perfect, of some finite characteristic of characteristic p, then you conclude that any irreducible polynomial, any irreducible polynomial f in fx is automatically separable. Okay, so in particular this holds for finite fields as well. Okay, now finally, coming to the point that we began at the very beginning, which is to talk about separable extensions. So far we talked about separable polynomials. When do we call an extension separable? Okay, so let's talk about separable extensions. So the definition is the following. We say that let K be an algebraic extension. So K over F be an algebraic extension. We say that this extension K over F is separable. So we say that it is a separable extension. So we assume to begin with that it is algebraic. It's only for algebraic extensions that we will define this notion. So we say it is a separable extension if for every element alpha in K, its minimal polynomial. So look at its minimal polynomial m alpha of x. Okay, so what is a minimal polynomial? So I'm talking about the minimal degree monic irreducible polynomial with coefficients in the base field. Okay, so what is a minimal polynomial here? Which I mean minimal degree monic polynomial in fx is not necessarily reducible with alpha as a root, right? So this is just the generator of the ideal on which alpha vanishes. If its minimal polynomial m alpha of x in fx is separable. So we talked about separable polynomials before. Now what we are saying is an extension is said to be separable if for every element of the extension, the minimal polynomial of that element over the base field is a separable polynomial. Okay, so let's quickly write out a corollary to our discussion of perfect fields and so on. The nice thing here is that recall if f has characteristic 0 or if it is perfect, then any reducible polynomial is automatically separable. Okay, so that gives us a rich class of examples of separable extensions. In fact, if the characteristic of the base field is either 0 or if f is perfect of some finite characteristic, then any algebraic extension is automatically separable. So then any algebraic extension K over F is separable. Okay, why is that? Because for every alpha, so what is it that we need? You take any alpha in K and look at its minimal polynomial. The minimal polynomial is always irreducible, and irreducible polynomials are automatically separable, okay, provided you have this hypothesis that the characteristic is either 0 or the field is perfect. Okay, so this is a rich class of examples. So for example, if your base field is a finite field, then any algebraic extension of a finite field is necessarily a separable extension. Or if you take the field of rational numbers, then any extension of Q, any algebraic extension of Q is automatically separable. Okay, so this is some nice thing to keep in mind. And in fact, the converse is also true. And so let me just state that for now. So we've already proved this, I mean, more or less as a consequence of what we said earlier. So I'm not going to prove the second part of this lemma. I'm just going to leave this as an exercise. Maybe we'll talk about it later in one of the problem solving sessions. If I mean, sort of the converse is true as well. If so, let characteristic of F be some prime P, then the converse holds. Every algebraic extension K of F is separable if and only if F is perfect. Okay, so it's really an equivalent statement. The field being perfect is exactly the property that says that all algebraic extensions are always separable extensions. Okay.